right. So these are some practice problems that deal with infrared and mass spectrometry. So the first question is, which of the mass over charge values corresponds to the base peak in the following mass spectrum? Well, a base peak is not necessarily the molecular ion, is it? A base peak is the tallest peak in a mass spectrum. So we're looking for the tallest peak. Therefore, this is going to be our base peak. So our base peak is this one here, which looks to me like it's got a mass over charge of 29, probably. Anyhow, that's a common fragment. So we'll say it's 29. Anyhow, the next one says, which one corresponds to the molecular ion? Well, if they're asking for a molecular ion, we're going to infer that there is a molecular ion, that there's a molecular ion in the for the molecule. So that would be the peak with the highest mass that is not an M+1 peak. And you can see that there is a tiny little M+1 peak, but that's not our molecular ion. That's a result of the isotope carbon-13, which is going to produce a small amount of an M+1 peak. And so this would represent our molecular ion. Let's move on to the next question. Question 3, it says calculate the degree of unsaturation, or the HDI, in this molecule or this molecular formula, C14H14N2O. And I showed you a couple ways that you could solve this problem. Probably the easiest way to do it is to use the formula. So HDI is equal to 1/2, 2 times the number of carbons plus 2 plus the number of nitrogens, subtract the number of hydrogens and the number of halogens. We can solve it that way. Or you could say, okay, well, for every nitrogen, I have an extra hydrogen. I have two nitrogens, so it's like I have 12 hydrogens. Then you have 14 times 2, which gives you 28 plus 2, which is 30. 30 subtract 12, and then you divide that by 2, and you get 9. So the answer would be 9. So 18 divided by 2 gives you 9. Same thing here. Again, you can use this formula to solve for the HDI, or the degree of unsaturation. So degree of unsaturation is the same thing as the U, or the HDI. And to solve here, it's like we have H10, because every nitrogen gives us an extra hydrogen. So if you have C9 times 2, that's 18. 18 plus 2 gives you 20. 20 subtract 10 gives you 10. 10 divided by 2 gives you 5. And so you have 5. All right. So the next question is, which of the mass over charge values correspond to the molecular ion for this compound? So remember, the molecular ion, okay, is going to come from the total mass of the compound. Now, we said that since this is an alcohol sometimes will not have a molecular ion. In fact, a lot of the times it won't have a molecular ion, but that doesn't mean that it won't have one all of the time. So a molecular ion always means the mass of the compound. So we're just looking for the mass of this compound. So we count up the number of carbons. We have 1, 2, 3, 4, 5, 6 carbons. So it's C6. If it's fully saturated, we have C6H14, and then we have 1 oxygen. So we tally up the mass. We have 6 times 12, which gives us 72, plus 14 plus 16. So that's 72 plus 30, which gives us 102. So that would be the molecular ion or the compound. Does that clear up your question about the molecular ion?
Yes.
Okay, good. All right, let's move on to the next one. It says, which of the following compounds will have an odd mass over charge? So we're looking for an odd mass, and that means we're dealing with the nitrogen rule. So if we have an odd mass means we have an odd number of nitrogens in the molecule. This molecule has no nitrogens, therefore it's going to have an even mass. This one has an odd number of nitrogens, therefore it's going to have an odd mass. This one has 2 nitrogens, therefore it's going to have an even mass. And this one has no nitrogens, therefore it's going to have an even mass. And so the answer is number 2, is the one with the odd number of nitrogens. 1 is an odd number, and therefore it's going to have the odd value for its molecular ion. Next one, we're looking for the presence of bromine in the compound. And you remember that bromine has 2 isotopes. We have bromine 79 and bromine 81. They are in a relative abundance of 51 to 49%, which is the same as, or pretty close to, a 1-to-1 ratio is what we should see for our molecular ion and our M+2 ion. So if you look at the top end of all of these, right, you can see that this one we have, you know, if we're going from 125, 26, 27, 28, 29, 30, 35. So 36, 37, 38. So we have 136 and 138, and they're in about a 1-to-1 ratio. So that means this would represent our molecular ion, and this would represent our our M+2 ion. If you look at the other mass spectra, right, you don't see anything like this in number 2. You don't see any, you know, isotopes where we have bromine present. Here, if this is our molecular ion, there's no M+2 peak to speak of, and the same thing here. So the answer is the first one would have bromine present in the molecule. If we move on to the next one, so it was number 1, so we'll circle that. Moving on from here, it says, which of the following compounds is consistent with the mass spectrum below? So this is where it helps to have the zoom tool for me, since my eyeballs don't work that well anymore. But if we have 70, go from 70 to 71 to 72, 73. So here we have a mass overcharge that is equal to 73, and this is our molecular ion. Okay, so there's the molecular ion, and it's got an odd mass. Therefore, it's going to have an odd number of nitrogen. So if we look at all of the possible compounds, the first one is just an alkane, right? The next one is an alcohol. The next one is an ether. So I'm looking for nitrogen. This one here is a secondary amine, and it's only got 1 nitrogen in it, so the answer is going to be D. So D has 1 nitrogen, and you can calculate the mass of this if you want. This is it's called diethylamine, okay? And if you calculate the mass of this compound, so it's C4, and then we have 1, 2, 3, 4, 5, so 10, we have a H11N, so that means we have 48. So we have 48 plus 11 plus 14, and that gives us mass or overcharge for our ion. Our molecular ion is going to be equal to 73. So we double check that one. The next one is one that I talked about quite a bit at the beginning of lecture today when we were talking about alcohols, because I said if you look up fragmentations of alcohols in our textbook, it tells you that the mass spectrum of an alcohol will typically, that doesn't mean all the time, but typically it doesn't exhibit a molecular ion peak, because alcohols readily undergo fragmentation in a mass spectrometer. And so since we don't have a molecular ion here, we have, again, we have an alkane here, we have an ether here, we have an amine here, but we have an alcohol right here. And if you draw out the structure of that alcohol, so I'll draw the bond line structure like this, okay? We can calculate the mass of this alcohol. It's C4H10O. So that means we've got 48. So we've got 58 plus 16, which gives us a molecular ion that would be equal to 74 for our molar mass. We don't have any 74 over here. So what kind of fragmentation could it do? Well, it could lose water, right? So loss of H2O, which has a mass of 18. So if we take 74 and we subtract 18, we end up with a mass overcharge of 56. We go over here, you can see we have, okay, we got 55. Boy, there's something there, but it's really small. So that's probably not one of the fragments, or it's a very small fragment. But you notice that we have an alpha carbon here. We have a beta carbon here, and then we have a beta carbon over here. Now you notice here that the 2 beta carbons are different, aren't they? Right, the beta carbon in green, if I cleave that one, what am I going to lose? I'm going to end up losing a methyl, so I'm going to end up losing 15. So if I take 74 and I lose the methyl radical, I end up with a mass overcharge that's equal to 59. Well, looky, I have that right here. I have a mass overcharge, which is equal to 59. If I cleave the one that's in red, so I'll use the red pen again over here. If I cleave right here, it's going to be a loss of 29, right? loss of my ethyl radical, loss of 29. So if I take 74 and I subtract 29, I get a mass overcharge that's equal to 45. And if I look over here, I see I have a mass overcharge of 45. So this is mass overcharge, which is equal to 45. And so this one is a result of alpha cleavage, and we're not asked to identify one. And this one would also be the result of alpha cleavage. So yeah, it's going to be our alcohol. And if you want to, spend some time trying to identify other peaks, so I wouldn't really stress about it a whole lot. All right, let's take a look at number 10. Which one of this mass spectrum is consistent with which of the compounds below? Let's look for the molecular ion here. So if we have, we have 70, 71, 72. We got a tiny little n+1 peak here. So this is our molecular ion, which is equal to, or has a mass overcharge that's equal to 72. So it's got an even mass. So that means I can scratch out D because D has an odd number of nitrogens. Now I've gone ahead and tallied up the masses of these compounds. The first one, A, is C5H12. So it would have a mass that's equal to 72. So that's a possibility. If we go to B, B has a formula which is C4H10. Oh, we looked at that earlier. So that has a mass of 74. And the next one, the ether, is the same thing. It's got the exact same formula, C4H10O, so that's 74. And then this one has an odd mass, so we're going to cross that one out. So the answer has to be A. It could only be that alkane there. All right. And if you draw the structure, and I'm, in the interest of time, I'm not going to go over all of it right now, but if you draw the structure of this compound, so that's 2-methylbutane, I mean, you could draw some fragments, right? You could calculate what would happen if you lose, 15 or 15 or 15, right? If you take 72 and you subtract 15, you get 57. And if you look over here, we have 55, 56, 57. So we have a mass overcharge of 57 here, which we would predict, right? What if you were to lose 29, right? Then you'd have a tertiary carbocation if you were to lose 29. So you take 72, subtract 29, and you end up with 43. It's kind of difficult to tell here with my prescription, but 41, 42, 43. So that would be this guy here. So this is a mass overcharge of 43. And again, we would predict that. So you could spend some more time analyzing those fragments if you want. Number 11, which of the compounds is consistent with the mass spectrum below? Same thing here. We have an odd mass for a molecular ion, don't we? Right? We have 100, 101. So our molecular ion is equal to 101. That's the mass overcharge. You can see there's a tiny little n+1 peak here. If it's got an odd mass, therefore it's going to have an odd number of nitrogens. That kind of makes things a little simpler, depending on what the possible answers are. There we go. So this one has an odd number of nitrogens. And if you tally up the mass, you have 3 propyl groups. So that's 43 times, no, sorry, you have 2 propyl groups, 43 times. I was like, that's not right. 42 plus 15, that gives you 101. So that makes sense that the molecular ion here would have a mass overcharge of 101. So it has to be the amine for this one. And again, this is another example where you could draw the compound out. So this is called dipropylamine. So you have 2 propyl groups. Now, what did I tell you? I told you that the carbon that's attached directly to the nitrogen, that's the alpha carbon. There's 2 alpha carbons. They're identical because there's a plane of symmetry down the molecule. But then you could identify the beta carbon, right? This is the beta carbon here. So what if you had alpha cleavage, right? That would be the loss of 29 if you were to break there. So if you take 101 and you lose 29, what do you end up with? 72. And lo and behold, there's a giant peak here at a mass overcharge of 72. So this is from the loss of the ethyl radical, right? Alpha cleavage. Okay, alpha cleavage, anyhow, of our secondary amine. All right, let's keep going here. Deduce the structure of the following compound. We have C3H3Cl. Remember that halogens are just like hydrogens in terms of the HDI. So this is as if you had C3H4. What would C3 be if it was totally saturated? It'd be 2N plus 2. So that'd be C3H8. So if you take 8 minus 4, you get 4. 4 over 2 gives you 2. So that means the HDI for this compound is equal to 2. Well, I'm going to start looking for areas of unsaturation. I'm going to circle a signal on here, okay? And notice that the scale here is a little different than the scales that we saw before. But if this is 2,000, right? This is 2,100 reciprocal centimeters. This is 2,200 reciprocal centimeters. If I have this big signal here at 2140 approximately. Exactly up here. I have this absorbance here at around 2240 reciprocal centimeters. Can anybody tell me what that would represent based off of what we saw in our infrared?
Nitrile.
It's not going to be a nitrile because in order for it to be a nitrile, right, if it was a nitrile, it's a good guess because a nitrile is a triple bond, right? And the nitrile absorbance is between 2260 and 2240, but we don't have any nitrogen in here. So it can't be that, but it's in the range of a triple bond, isn't it, right? So if we look at an alkyne is in the neighborhood of 2150 to 2100, right? So this is a little bit outside of that, but remember that when you're looking at values, okay, so if we look at the value for a carbon-carbon triple bond, if you look at our table, it says 2150 to 2100. But remember, you have to take these values with a bit of, leeway to them. So it must be an alkyne. It's the only possibility, right? And also, that would produce 2 units of unsaturation, right? If you have a triple bond, because in a triple bond, you've got 2 pi bonds. So that would cover your HDI of 2. Another dead giveaway that this would be an alkyne is that you have this huge absorbance here. So if you follow the scale, it goes from 3,200 to this is 3,300 reciprocal centimeters. And for an alkyne, if it's a terminal alkyne, we also see a sharp absorbance for the sp hybridized carbon-hydrogen stretch. So that tells you that this must be a terminal alkyne, right? It's got a hydrogen attached to the end. So that means that we've got this so far. We've got a carbon-carbon triple bond with a hydrogen. So far out of C3H3Cl, we've got 1 carbon left over, we've got 2 hydrogens, and we've got the chlorine left over. There is literally only one possible way that we could arrange those elements attached to this piece, which we know we have. The only possible way we could arrange that is to have CH2 and then to have a chlorine like this. So this would be the molecule. So this would be 3-chloropropyne. Again, we have the absorbance for the carbon-hydrogen sp hybridized carbon-hydrogen stretch. We have the absorbance for the carbon-carbon triple bond right there. All right. The next one. So the next one, you can't help yourself. I can't, just by opening up the problem and just saying, well, it's probably an alcohol, right? I see that I have a big oxygen-hydrogen stretch here, right? And then I have an oxygen in the compound, okay? The next thing I could do is determine the HDI since I have C7H8O. If I have a fully saturated C7, it would be C7H16. So if I take 16, subtract 8 divided by 2, I get 4. So that means my HDI is equal to 4. Again, you could use the formula. I'm just doing a shorthand of it. So how would I have 4 units of unsaturation? Well, I want to zoom in on a particular part of the spectrum here. If you look between 1600 and 1450, so if I get out the ruler here, so if we look between 1600-ish, okay, and 1450, which is right around, oh boy, right around here, okay, when we have an aromatic ring, we will usually see 2 to 3 absorbances in the range of 1450 to 1600. Now you can see that we've got one here. We've kind of got one here that's kind of not super sharp. And then we've got another one here. Usually the three, if you have three signals or three absorbances in the aromatic region, they'll usually be at 1450, 1500, and 1600. They're usually kind of like that, not all the time. So that's why it's not in our book, because you can't really hitch your wagon to that 100% of the time. But I want to propose that if we had an aromatic ring, right? First of all, the six-membered ring is 1 unit of unsaturation, 2, 3, 4. So an aromatic ring has an HDI equal to 4. So there we go. Now we've got an alcohol and we've got an aromatic ring, right? This is what we know so far, okay? Just recapping, we've got a hydroxyl and we've got an aromatic ring. Okay. Well, there's some other things that we could do here. We could also draw a line at 3,000 reciprocal centimeters, which is right around here. I'm going to use the green pen here. So we could draw a line there, okay? And notice that we do have some stretching right above 3,000. What would that be? That is from the sp2 hybridized carbon-hydrogen stretching, right? Because we're going to have sp2 hybridized carbon-hydrogen bonds on our aromatic ring. Okay, that doesn't get us a whole lot farther, but there's one more thing that might not be as intuitive to you. It's that we've only got 7 carbons in the molecule, and if 6 of them are in the aromatic ring, look at this. I'm going to use the red pen here. We've also got some stretching right here, which is the result of sp3 hybridized carbon-hydrogen stretching. So that tells us that the 7th carbon, right, because there's 6 here, there's one more carbon, and that carbon must be sp3 hybridized, right? It's got to either be a CH2, or it's either got to be that, or it's got to be a CH3. It's got to be one or the other, right? So what are some possible ways that I could put all this together? Okay, I've got my aromatic ring. Let's write down what we've got. We've got our aromatic ring, okay? We've got another carbon that is sp2 hybridized, okay? Sorry, sp3 hybridized. So it's going to be a methyl group or a hydrox, or a methylene. Sorry, I'm thinking about too many things at once here. And we have a hydroxyl. So one possible way that you could put all this together would be to have something that looks like this. Would be to have an aromatic ring with a methyl group on it, and then a hydroxyl like this. In terms of the arrangement of the methyl group and the hydroxyl, it could be like that. It could be like this, okay? It could be like this. And are there other possibilities? Yeah, I'd say there are other possibilities. You know, there is another possibility. What if you connected it like this? Okay, I'd say that's also a possibility. Okay, so there's several possibilities here. So this isn't, you know, wouldn't make the greatest multiple choice question, but I would say that all of those would be possible based on the information that we are given. All right. So the next one is matching the infrared spectra with all of these isomers. The next one is in the same vein. It's matching infrared spectra with all the isomers. The next ones are questions that come straight from the book. Let's try one more problem, and then we're going to have to move on to chapter 5. Which one's better? This one's kind of a cool one because they're all isomers. It's kind of neat. Just proof, you know. If you were given just the molecular formula, and there's so many possibilities, you know, you couldn't just say, oh, it's going to be an alcohol. It might be an alcohol, it might be a ketone, might be an ether, might be an aldehyde, right? There's a lot of different possibilities here. Well, let's see if we can determine, you know, which one of these infrared spectra. So we'll call, they're labeled kind of funny, aren't they, right? This one here says A, this one says B, this one says C, this one says D, and this one says E. Who put that together? Anyhow, so they're all labeled kind of funny here. But let's see if we can figure it out. You know what? I like to go with the low-hanging fruit first. I find it's the easiest thing to do. Let's start with the 2 alcohols. Could anybody tell me which spectra they think might be alcohols? And I can relabel these so you can see it a little bit better. So this one is B, this one is A, this one is E. I can't even see it. This one is C, and this one is D. Could anybody tell me which spectra they think might be alcohols? Yeah, absolutely. Yes, you're all 100% correct. It's C and D, right? See, it's nice to go for the low-hanging fruit, as I call it, right? I'm sure that all of you, every single person in the class probably looked at these and just said, hey, come on, that's an alcohol, right? So that, we've already covered a couple of things. It makes the problem a lot simpler. You could just label these as an oxygen-hydrogen stretch, oxygen-hydrogen stretch. Anyhow, now let's go back to the two alcohols. So we have cyclobutanol, and then we have this alcohol over here. Well, the other alcohol, this one has an alkene in it. So we should see a carbon-carbon stretch, and we should also have sp2 hybridized carbon-hydrogen stretching, which wouldn't be present in the other. So if I compare C and D, could anybody tell me which one of these, C or D, has the alkene in it, and it's not a trick? Even though the numbers are faint, you should still be able to kind of tell, I hope. I guess it might depend if you're watching the lecture on a cell phone or something. Yeah, it's D. D is the alkene. Let me show you why. Okay. Let's take the ruler here. And if we put the ruler at 3000, and again, it really helps to be able to zoom in on these. Again, I've told you this 100 times, my eyesight isn't that great. But you can see that there's something here, right? This little nub here, that is actually the sp2 hybridized carbon-hydrogen stretching of the alkene. But what do you see that's a lot more obvious? If this is 1500 right here, the carbon-carbon stretch, carbon-carbon double bond stretch of an alkene is around 1630. So this is 1600, this is 1650. So it's in that neighborhood, right? This is the carbon-carbon double bond stretch, okay, of the alkene. So this one must be the alkene. Let's get rid of the ruler. And so C would be the cyclobutanol, and then D would be this one here. So 2 already done. I'm going to throw this out to my students who are all good problem solvers. I know you are. I can tell by the way you guys answer questions. Between A, B, and E, because we've already figured out this one, we're done, and we're done here. Hey, I'll just throw it out there. Does anybody have a thought? And if you need to unmute your mic or just if you just want to type it out, does anybody have a thought about which is which for any of these? And it's not a race or anything. I'm just curious. Let me maybe ask a question a different way. Between B, A, and E, personally, now everybody's different. It's really hard to see the points on the scale. So around this point here, okay, for all these, this is 1500. Okay, so this is 1500 right around here. Okay, and then this is 3000. Okay, so this is 3000, and this is 1500, and this is 1500, and this is 3000. Okay. Okay, so I would recommend if you have a computer, you could zoom in on them. Okay, there we go. Anyhow, so if we take a look at these, let's go with A. Let's start with A. I've got either an aldehyde or a ketone or an ether. Okay, would A be an aldehyde, ketone, or an ether that has an alkene in it? Could anybody identify A? If we draw a line, get the ruler at 3000. Okay, get the ruler here. Draw a line at 3000. Draw a line at 1500. All right. Here we go. Well, at around 3,000, if you look just below the 3,000, you notice there's two peaks right here. Okay. So these are at around 2750 and 2850 reciprocal centimeters. This is aldehydic carbon hydrogen stretching, is what you're seeing here. So when we have our aldehyde, so this is this carbon hydrogen stretch. Okay, and then here we have the carbonyl stretch. So that means that A would be the aldehyde. So A would be this aldehyde. If we go over to, if we compare B and E, well, B has a carbonyl in it, right? This one has a carbonyl, whereas if you look at E, E does not have a carbonyl in it, but it does have a carbon-carbon double bond stretch, okay? Right above 1630. So this would end up being our ether, like this, and then this one would be our ketone. So this would be the butanone like this. So this would be B, and then this one would be E. All right.